Hi everyone. In this video we're going to talk about coupling constants, and then we'll also talk about chemical shift. So where do peaks show up on an NMR spectrum and what influences their location? So last time we talked about spin-spin coupling and how neighboring protons can split each other, so you can end up with doublets, triplets, quartets, etc. But let's talk about the distance between those peaks. So coupling constants, which are also called J values, is the distance between peaks when a peak is split. So let's just write down that definition. And the distance between these peaks will be in units of hertz, so frequency. So let's look at an example. Let's say we have a carbonyl or a ketone, and let's say there's just some R group off to the side there. So we have two different types of protons here. We have HA, which is on the left side of the ketone, and then HB, which is on the right side of the ketone. Okay, now what type of, or I guess what would the multiplicity be for HA? So do we expect it to be a singlet, a doublet, a triplet, a quartet? So let's see how many neighboring protons HA has. So if we go 1, 2, 3 bonds away, we have HB. And there are 2 HB protons. So using our n+1 rule, we would get a triplet. All right, so let's see what these coupling constants are. So let's say HA was just on its own. We would just have a singlet. But in this case, there are 2 HB protons next door. So HA is going to be split by 1 HB proton first. So that will result in 2 peaks there. And the distance between these we'll call JAB. So that's our coupling constant. Now in this case we do have 2 HB protons. So these will be split one more time each. So we end up with a total of 3 peaks. So that's our triplet. And the distance between those peaks down below is also JAB. All right, and that will give us our triplet. Let me just make some room here. So we would have a peak here, a larger peak in the middle due to that 1 to 2 to 1 ratio we talked about last time. And then we have our other peak off to the side. Okay, so again, that J value is the distance between peaks when a peak is split. So let's look at another example. Let's say we have an alkene, and on one side we have a fluorine and a hydrogen. On the other side we have a chlorine and a hydrogen. How many unique protons do we have? 2, because one hydrogen is closer to fluorine, the other hydrogen is closer to chlorine. So we have HA and HB. Now, how many neighboring protons does HA have? Just one, and it is 3 bonds away, so that works. So what is the multiplicity of HA, or what do we expect the multiplicity to be? A doublet, because we have one neighboring proton, and the n+1 rule would tell us that we have a value of 2 there, so that is a doublet. What about HB? What multiplicity would we expect for HB? Also a doublet. Okay, so if we look at the doublet for HA, we would have a specific difference between, or a specific distance, excuse me, between those two peaks, and we would label that JAB. So HA split by HB. And then if we look at the doublet for HB, that would have its own distance, JBA. And that is HB split by HA. But actually, these will be the same distance. So JAB will equal JBA. Now let's look at a weird example. So let's say we have a similar alkene. So we've got a fluorine and a hydrogen on one carbon, but this time we have 2 hydrogens on the other carbon. How many unique hydrogens do we have? 3. So we have HA and HB like before, but the third hydrogen is actually not equivalent to HB because HB is trans to fluorine and the other hydrogen on top is cis to fluorine, so that makes them different. So I'm going to label that HC. Okay, so now what is the multiplicity of HA? So how many neighboring protons does HA have? 2, HB and HC. So what would we expect the multiplicity to be? A triplet. But remember, I said this was a weird example. So we're expecting a triplet, but what actually happens, so let's see, we've got our peak for HA when it's not split. And then it will be split by HC. And that has a distance of JAC, so HA being split by HC. And then HA will be split by HB, but that's going to have a different distance. So what we end up with is 4 peaks, even though we only expected 3. And that's because the splitting distances are different for HC and HB. So what we end up with kind of looks like a quartet, but it's not really a quartet. It's actually going to be a doublet of doublets. So we have one doublet, and then another doublet, and it's a doublet of doublets. So it's kind of a weird example. Now, this could show up as a multiplet depending on how well they're separated. So if they're not separated very well, it can look all jumbled and it will come out as what's called a multiplet. So a multiplet will kind of be like a jumbled mess. It might look something like that, where you get these kind of noisy peaks that don't really make sense. They don't follow a particular pattern. And it kind of just depends on how accurate your instrument is and how well it separates peaks. All right, so if you do see this doublet of doublets where you don't have a traditional quartet where the 2 middle peaks are really tall, then you might have a situation like what we saw here where you have an alkene maybe, or you just have 2 different hydrogens next door. So just keep that in mind. All right, so now we're going to move on to chemical shift. So chemical shift is that ppm value, so where peaks show up on the NMR spectrum. So chemical shift is given a lowercase delta symbol, and there's actually an equation for chemical shift. Now, chemical shift is going to be relative to what's called the TMS peak. So TMS is a reference compound that we use. I'll draw that in a second. Now, this is all going to be in units of hertz, so it's in radio frequency. Now we're going to divide this observed shift from TMS, our reference compound, by the operating frequency, or we're dividing by the operating frequency of the instrument, which will also be in hertz. So instruments can have different operating frequencies. They can be, for instance, you might have an operating frequency of 300 megahertz. You could have an operating frequency of 60 megahertz. Again, it kind of depends on how strong your instrument is or how strong the magnets are in your instrument. So again, TMS is a reference compound. And we kind of calibrate our instrument based on where TMS shows up. So TMS is tetramethylsilane. And it looks like the following. So we have a silicon atom in the middle, and then we have methyl groups surrounding it. So usually what we do is we add TMS to our sample, and it shows up, or it should show up at 0 parts per million. Now, if it shows up maybe a little bit off of 0, then we just calibrate so that it shows up at 0. All right, now let's look at some examples of how we would figure out the chemical shift. All right, so let's say that we have benzene. Now, if benzene is being analyzed on a 300 megahertz instrument, then it's going to absorb a frequency of, or a radio frequency of 2,181 hertz larger than TMS. So what we would do is we would use that fact and we would divide that by the operating frequency of the instrument, which I said was 300 megahertz. Now, we obviously need to convert that to hertz, and I'll just do that for you. It's going to be 300 times 10 to the 6th hertz. And if we plug that into our calculator, we get a value of 7.27 times 10 to the negative 6th. Great. Now, this will be different on a different instrument. So let's say instead of a 300 megahertz instrument, we use a 60 megahertz instrument. Now, in that instrument, benzene is going to absorb a radio frequency that is 436 hertz larger than TMS. And these are all values that have been measured before, so I'm not just coming up with them out of thin air. They're just frequently measured values that have been done in the past. They might seem kind of arbitrary though, like I'm just kind of pulling them out of my head. Okay, so let's see, 60 megahertz would be 60 times 10 to the 6th. And if we plug that into our calculator, we're going to get the same exact value that we got before. 7.27 times 10 to the 6th. And this is in parts per million. Oh, parts per million. So it really doesn't matter what instrument you use. The chemical shift of your compound is going to be exactly the same. So whether you're using a 300 megahertz instrument or a 60 megahertz instrument. So this is why we use parts per million instead of hertz, because that relationship between where the shift from TMS to the operating frequency of the instrument should be the same. All right, so we get these predictable shifts for different functional groups. So let's look at where we expect certain protons to show up on an NMR spectrum. So this is a chart that I've also posted under modules study guides. And you can use this to help you figure out where to expect certain peaks. So down below, we have our parts per million range from 0 to 12. So 0 is on the right-hand side, And you'll notice that's where TMS, our reference compound, will show up. And again, that's how we calibrate our instrument. Now, you'll also notice that the lower values here are called, or are referred to as upfield. So if a peak is upfield, that means it has a lower value. And then if something is downfield, so in the opposite direction, that means it has a higher value. Now that has to do with whether the nuclei are quote unquote shielded or de-shielded. So we'll talk about that in a little bit. But notice that, so if we go all the way downfield, carboxylic acids have a proton on that oxygen. And peaks for carboxylic acid protons will show up anywhere from about 10 to 12 ppm. Now, aldehyde protons, their peaks will show up anywhere from 9 to 10 ppm. On the last slide, we talked about benzene, and we said that its protons would show up at about 7.26 ppm. And you'll notice that there's actually a wider range here. So from 6 to 9 ppm, that's where the benzene ring protons will show up, or aromatic protons, they're called. All right, and then as we move further upfield, we can see that alkene protons will show up anywhere from about 4.5 to 6 ppm. Then we have protons that are bonded to a carbon that's bonded to a halogen. And those can show up anywhere from 2 to 4 ppm. And this is where things start to get a little confusing because there's a lot in this area, in this region. So we have ketones and the hydrogens that are bonded to carbons on a ketone. These are sometimes referred to as aliphatic ketones. So if you see that term aliphatic, it refers to the hydrogens on the carbon next to a ketone. It's kind of confusing. We also have alkyne protons and alcohol protons. And the alcohol protons span a very wide range. So it starts to get a little hard to interpret upfield. Now, if you do see a peak from 0 to 2, that's most likely just a regular alkane proton. So what you might notice is in the downfield region, so in the higher value region, we have a lot of carbonyl groups, so oxygens, etc. And those are very electronegative. So let's just write En here for electronegative. And that's going to have an effect on where your chemical shift is for a peak. So the more electronegative something is, the further downfield it is. So for instance, our halogen is a little more downfield, or the proton that's bonded to a carbon that's bonded to a halogen is a little more downfield than an alkane hydrogen. You'll also notice that the aromatic groups have an effect on where the peak will show up as well. So let's just talk about those two different factors. So factors that affect your chemical shift are, one, the inductive effect. So we talked about that last quarter. And then two, something called anisotropic effects or anisotropic effects. I forget how it's pronounced. So let's talk about the inductive effect. So this really has to do with, for instance, electronegativity or electron withdrawing groups. So what happens here is atoms like oxygen or halogens, they're going to draw electrons away from protons. And this is going to de-shield the proton. So it moves the peak or the signal downfield. So there's this shielding effect that electrons have around a nucleus. And if electrons are kind of pulled away from a nucleus, it de-shields the nucleus. So looking at our NMR spectrum here, again, if something is de-shielded, it moves downfield or it has a higher value. And if something has electrons around it, so if a proton has more electrons around it, it will be shielded and it will be more upfield. Now let's talk about these anisotropic effects. So this has to do with double bonds. All right, so let's talk about a benzene ring, for instance. So a benzene ring, remember, has double bonds. So that means it has p orbitals all the way around the ring. And remember, the electrons are delocalized across all of those pi bonds, and that's above and below. Now, what this does is it induces a magnetic field. Okay, so as those pi electrons are kind of circulating around the ring, that causes that magnetic field, and that's going to de-shield the protons that are attached. So the protons are kind of sticking out beyond the magnetic field, and they'll be de-shielded. So these will be shifted downfield. So if we look at our chart on the last slide, again, any aromatic protons or benzene protons are pretty downfield. They're between 6 and 9. And again, that's just due to the fact that the protons are de-shielded by that magnetic field that's generated from the delocalized electrons. Now, you don't necessarily have to remember all of these little details, but just be aware that that's why peaks show up in different areas on our NMR spectrum. It has to do with either electronegative atoms drawing electrons away from the protons, or this magnetic field from our delocalized electrons. Okay, now let's talk about how we can predict some chemical shifts. And this has more to do with electronegative atoms. So this chart is in your book. If you have the third edition of the textbook, this will be chart 15.3 instead of 16.3. So what we can do is assume that methyl protons will show up at about 0.9 parts per million. Now, if you have a carbon that's kind of in the middle of a chain of carbons, we call that a methylene group. So methylene protons will show up at about 1.2 parts per million. And then let's say you have a tertiary carbon. Its proton will show up at about 1.7 parts per million. So we call this a methine group. Now, what if we have a methylene group next to an alcohol or an ether? Could be alcohol or ether. What we'll do is we'll add 2.5 to our expected value of 1.2, and that will give us an approximate idea of where those protons will show up on an NMR spectrum. Now let's say we have that same methylene group, but instead of being next to an alcohol or an ether, let's say it's next to an ester. We're going to add 3.0 to our expected 1.2 value, and that gives us an approximate value of 4.2 parts per million. So that's where we would expect that type of proton to show up. And then what if the methylene group is next to a carbonyl group? So that could be on a ketone, for instance, or an aldehyde maybe. That will show up, or I guess we're going to add 1 to our expected value, and that will show up at 2.2 parts per million. So let's look at an example of this just to kind of tie it all together. So let's say we have an ester, and there's ethyl groups on either side of the ester. Now let's look at the 2 protons on the left side and the 2 protons on the right side. So the protons on the left-hand side are next to a carbonyl group. Okay, and then the protons on the right-hand side are next to the oxygen of an ester. So they're in a different chemical environment. So even though both sets of protons are technically next to an ester, you have to think about the difference in those oxygens. So for instance, HB is next to an oxygen on an ester, but HA is next to a carbon on an ester. So they're slightly different. So they are in different chemical environments. So now let's see if we can predict where these will show up on an NMR spectrum based on our diagram up above. All right, so HA is part of a methylene group. So we would expect it to normally show up at 1.2 parts per million, but because it's next to a carbonyl group, we're going to add 1. So we would expect this to show up at 2.2 parts per million. So again, it's next to a carbonyl group, so we would add 1. Now, what about HB? So again, it's part of a methylene group, so normally we would expect it to show up at 1.2 parts per million, but it's next to the oxygen of an ester. So we're going to add 3. So that would give us 4.2 parts per million. Now notice that HB is more downfield, or it has a higher ppm value than HA. And that's because HB is right next to that oxygen. So the oxygen is withdrawing electrons. But HA is a little bit more removed from that oxygen, so it's going to be more upfield. It's not quite as affected by the oxygen atoms as HB is. So distance from an electronegative atom also plays a part in chemical shift. All right, so let's kind of draw a little NMR spectrum. So we would expect HA to show up at around 2.2 parts per million. Now, what would its multiplicity be? So how many neighboring protons does HA have? So on the methyl group on the end, there are 3 protons. So HA would have 3 neighboring protons that are in a different chemical environment. So would we see a singlet, a doublet, a triplet, a quartet? A quartet, because of the n+1 rule. So it has 3 neighboring carbons plus 1. That is a quartet. Now HB we're expecting to show up at around 4.2 ppm. And how many neighboring hydrogens does HB have? 3. It has that methyl group next door. So it would also show up as a quartet. All right, so we've got HA and HB, and they're both going to show up as quartets. But their chemical shifts are different because of their position on the molecule and how close they are to specific groups. And I would give you this type of information on an exam. So I would give you, for instance, this chart on an exam, so you could try to line up peaks with specific functional groups and their protons. I would also give you this chart as well, so you could kind of predict where peaks should show up, either upfield or downfield. Now, one last thing we have to talk about before we end our chapter is carbon NMR. So remember, we can use NMR with all sorts of isotopes as long as they have an odd number of protons and neutrons in the nucleus. So carbon-13 NMR and then proton NMR are the 2 most common types. Now, carbon NMR is less sensitive than proton NMR. Oh, I still have my highlighter. Let's switch that. So remember, carbon-13 is only 1.1% naturally abundant. So it's a little more difficult to get a reading on those carbon atoms, whereas protons are, super abundant. They're everywhere, or at least hydrogens with a mass of 1. So it is difficult to see or difficult to detect carbon-13. Now, in carbon NMR, there's usually no splitting like we have with protons. And we don't typically integrate the peaks. And that's because the area under a carbon-13 peak isn't really useful. However, what is useful about carbon NMR is it tells us the number of unique carbons we have. And the chemical shift will tell us what type of functional group we have. So on the next slide, I'm going to show you a similar chart to the one we saw before, but this time it will be for carbon-13 NMR. And you'll notice that the part per million scale is different. So for proton NMR, it went from 0 to 12. For carbon NMR, it goes from 0 to 240. So it's a very different scale. But you can see that we kind of have similar relative positions for different functional groups. So carboxylic acids, ketones, and aldehydes, they all show up around 160 to 220. Esters show up at around 160 to 180, and this would be specifically the carbon in those functional groups. Amides also show up around that range. Nitriles will show up a little bit upfield, so around 120 to 140 parts per million. But also also in that range are alkenes and benzene carbons. Now, as we move more upfield, so to lower values, we start to see carbons bonded to a halogen, so alkyl halide carbons, carbons bonded to nitrogen, to oxygen, and then we just start to see some regular alkane carbons. But you'll notice that primary carbons show up more upfield from secondary carbons, which are more upfield from tertiary carbons. So I will also give you this chart on an exam so that you can use it to try to figure out, where peaks will show up on a carbon-13 NMR spectrum. And then you can try to kind of figure out what functional groups you have in your structure. All right. So in the next video, we're going to go over some practice problems. So we're going to use proton NMR and then carbon-13 NMR to figure out the structure of different molecules. So I will see you then.